So Anna, you should be able to unmute your microphone and your camera now so we can see you.
Super.
Perfect.
Hi.
So yeah, as you know, the Lego Group is a global leader in the toy industry, and it's constantly pushing forward the boundaries of innovation and creativity. This is why I'm really excited that we are kicking off this morning with Anna, because Anna is a senior additive manufacturing engineer at the Lego Group. So Anna will be sharing some really unique insights about the work that her team is doing. And at the very end, you can also learn about some interesting job opportunities available at Lego. So good morning to Denmark. Anna, how are you doing?
I'm great. Yeah, I'll share my.
Fantastic. So whenever you're ready, you just share your screen and your presentation, and then you are ready to start. And feel free to ask questions in the chat that we can ask Anna later on. Thanks. Annie, the stage, Anna, the stage is yours.
Great. You can see my screen okay?
Yes, I can see it perfectly.
Awesome. Okay, so welcome. Today I'm going to talk about some design tips and tricks that I use in my role as part of as a senior additive manufacturing engineer at the Lego Group. Specifically, I'll talk toward what our department is about, our department, Additive Design and Manufacturing, AD&M. I'll do an intro to the technology, AM technology under the Lego roof. I'll talk about the type of criteria that's necessary for all Lego elements to pass, including our AM elements. I'll talk towards some design tips and tricks for cleaning AM parts from support material. I'll talk about the importance of orientation for design thinking, how parametric build jobs have really improved our ability to iterate quickly. And I'll just briefly touch on some job opportunities, but there's a career fair later on at this event that you can find one of my colleagues that will be talking more toward that. Great. So first, additive design manufacturing, it's made of two halves. One is AM of equipment, so that's literal AM parts that are used for jigs and fixtures, a part of our production. And then there's AM of consumer goods, and that's where my talk today will be focused. So that's literal elements that are mass manufactured using additive manufacturing. Yeah. So why are we doing AM at Lego? There's a number of benefits, but three of which are, of course, these elements are impossible to mold. So this is the Brandenburg Gate element of a mock of the Brandenburg Gate in Berlin. And so you can get some like very interesting sculpted detail that would be impossible to injection mold. It's just an example of that. We can also do functional elements, elements that have unique functions that have consolidated parts. So in this example, this is a suspension element that, you know, in a normal Lego element, a suspension is 3 or 4 parts that's factory assembled. So this having them all consolidated just brings more opportunity to the group. Also, we have the ability to customize parts. Think about in the future, maybe you have the option of making your own Lego wheel, and maybe you can have 10 spokes or 20 spokes. Maybe you can have your name on it. These are some of the unique opportunities that AM presents. So what have we been up to? Our team produced its first Lego 3D printed element back in 2018 as part of the Lego Inside Tour set. This is an architect's arm. It has a very cute compliant spring in it that allows it to articulate on this architect's desk. So that was our first element. Our second element was just released in the fall of this year, and it was an exclusive duck made for the Lego House, which is the main Lego museum here in Denmark. And it's kind of a throwback to one of the first Lego toys, which is this wooden duck pull toy. And when this duck is rolled, you can see how the beak moves up and down. Very cute. Third, very shortly after the duck was released, there was a gift with purchase of an AM pogo stick as part of a gift with purchase with this book, The Secret Life of the Lego Brick. Oh, again, it's consolidated features within one part. And yeah, that's a bit of a summary of the consumer goods. Now for the manufacturing equipment, we do parts like these, which are jigs that allow you to fasten an element in place when, for example, the element needs some pad printing or some paint applied to the face of it. So these are two different pad printing elements made in AM. Yeah. So we have a number of technologies under the roof at LEGO, and these different technologies solidify material in different ways. So for example, FDM melts a layer of resin layer by layer with a hot extruder. In selective laser sintering, or SLS, we have nylon powder, which is spread into a thin layer and sintered by a laser. And this repeats layer by layer. I'll talk more toward this technology later. We have polyjet, which uses liquid droplets of resin that are extruded and cured layer by layer. And then lastly, we also use SLA, which is there's a liquid resin in a bath, and by this bath or this bed kind of moving upward, there's a curing layer by layer that happens there. Yeah, so as I mentioned, there's going to be a special focus today on selective laser sintering, SLS, and polyjetting. So I'll just go a little bit more detail into the process. So as I mentioned, in SLS, there's a layer of powder that is spread across a bed of material. And then once the layer is spread, it's cured by a laser. And then once that curing happens, this bed is kind of drops down the height of a single layer. And then more powder is spread across, the laser cures it, and this process kind of repeats. And what's important to note, because I'm going to be talking about cleaning today, is, when the final part is finished, it still has a bunch of powder attached to it. It doesn't just come out clean. So there's a series of processes that take place that allow the part to get cleaned. So as I mentioned, also talk about polyjetting. And in this process, droplets of resin of part and support material are deposited in one layer. So you can see here, these little droplets coming down. And once these droplets of material are laid down, they're immediately cured by a UV lamp. And this process repeats itself. Now, again, here's a picture of the part with support material on it, and then after it's cleaned with the support material moved, and the support material is very, very soft and relatively easy to remove. And so, yeah, that's just one of the reasons why I'm talking about it today. Yes, so now I just want to talk about the criteria that every LEGO element needs to pass, not just the AM LEGO elements. So first of which, all of our elements go through rigorous product safety testing. So, applying different tensions, compressions, drop testing, seeing if there's sharp points that are created. That is what all of our elements go through. Also, there's more of a subjective quality review that's done to the elements. So, literal feeling, is this element feel too wobbly? In the case of the duck, does the beak open enough for it to be visible? Yeah, so that kind of a review. And these are important because we also need to make sure that our final elements are fully cleanable of all support material. And in order for it to not be too wobbly, we have to make sure our gaps are correct. So that's why I mentioned that. Also, all of our elements need to align to the LEGO DNA. And what I mean by that is, in very early iterations of the duck kind of looked like the one-to-one duck that you saw. I had pictured that wooden pull toy. And this doesn't align with the Lego DNA because in the Lego DNA, all Lego animals have like a very specific chamfering or like flattening of the edges and kind of look a bit cartoonish. So yeah, this design had to undergo that kind of change in order for it to fit. In addition, all of our elements have very specific surface roughness and color requirements. Here's a plastic ABS plate with the different Lego surface finishes, from highly glossy to kind of a surface roof tile roughness. And again, we have to make sure our elements align to one of these. It's also important that all of the Lego elements fit within system or within grid, we call it. And you can see that here's kind of a picture of a grid showing the different modules. And if a Lego element doesn't fit within this specific module grids within these specific dimensions, it's going to throw the whole Lego system off. So we really had to make sure that our final duck was also within system. You can see this connector here that fits into a minifigure hand, kind of aligned to that grid, as is like the whole outline of the duck was within grid. And lastly, we have to make sure the Lego logo is visible. Yes, so when I talk toward design tips today, I'm talking about printers with support material that's easily removable. So again, the SLS and the PolyJet. I'm not talking about printers that have support structures. So just keep that in mind. Here's an example of an FDM printer in SLA. Yes, so first and foremost, we want to increase openings in the element to allow for the cleaning of support material. But we can't just swish tease our element. We have to make sure that these openings are small enough that they don't impact the Lego DNA aesthetic. They don't impact our product safety test. They don't make it too wobbly. So it's kind of this big balance between how much do we open the element, how much do we open the element, and how much do we not, just to make sure that these we can maintain the criteria. Also, when designing these openings or these gaps, we try to decrease our context surface area in the gap. And what do I mean by that? So for example, if I want to make a piston or a hinge, maybe even the axle to the wheel here, instead of just doing a circle piston within a larger circle, there's not as much room for cleaning in this area. So it's preferred if you make a Y extrude or an X extrude that allows for more cleaning holes. And you can see each of these in this fixture, all of the dimensions are the same between the top and the bottom. And there's actually, in these holes, there's a lot more support media that's kind of stuck between them. Whereas when you're opening it up a bit more, then you can clean a bit better while still maintaining the same function, and you're not having a lot of wobbliness. You can also change process parameters in the machine itself to improve the cleaning, but I won't be going into that today. Yes, so I wanted to put this in context. So I took an element that one of the designers gave me, who's used to designing something for injection molding. And he wanted to make this clock function. So by turning this bit outside, he wanted the clock hands to turn with the mechanism of having these gears to allow that function. But the design was a mess for AM, right? Because there's a lot of flat surfaces. There are a lot of narrow channels, very difficult to clean. So I used some of these design methods to improve the cleaning. So here is the most optimized design. And you can see that I decreased the contact surface area in the gaps. So what does that mean? You can see I kind of use that Y extrude I talked about, like in this hinge area here, or I use little spheres between this outer face and the face of this kind of wheel here. And the spheres, again, they prevent the whole element from being very wobbly, but still open up the gap enough to allow for cleaning. And then also you can see I changed kind of these flat surfaces here, big bulky flat surfaces to tubes. So again, that there's better room for cleaning. And the final element is beautiful working element. You can see the turning happening, the clock ticking, and the gears moving. Yeah. Boom. So that's a little bit about design, but I also want to talk about part orientation and how that has a major impact on the final quality of your part. So, for example, the part orientation impacts the surface roughness, it impacts the strength, it impacts the dimensional accuracy, and then these in turn impact all of the criteria I mentioned previously. And when I talk about orientation, again, I mean, is the part laying down flat on your print bed? Is it standing up? Is it at a different angle? So I'll talk a little bit toward this. Yes, so first I want to talk about roundness and part orientation. And first I'll talk about roundness as it relates to SLS, selective laser sintering. And so when you're orienting your part and you want to make a circle, for example, it's easier to position this circle relative to the XY plane because that's the plane that the laser has the easiest time kind of following the circular pattern while it's sintering the cross section. However, it's much more difficult to get a perfect roundness when a part is printed on the ZX or the ZY plane. You can kind of see here there's a bit of like an egg shape or like a kind of an ovular shape in these holes. Why does this happen? And it's this effect called overcuring that causes this to happen. And essentially what overcuring is, let's say you have your CAD part. This is the Z-axis, so right here. And you want your CAD to print perfectly on layer 1 and then layer 2 and layer 3 and then build up your CAD part over time. It's not as simple as that. So when the laser hits layer 1, boom, it doesn't just hit layer 1, it hits that layer plus a layer and a half below it. And why does this happen? It helps because in layer 2 and 3 and so on, this kind of overcuring effect kind of sinters those layers together and makes it stronger, but it doesn't really benefit your very first layer because it's just sintering into empty layers and kind of creating this bowling effect. So you can see here in the clock element, you kind of have that bowling effect shown here and that ovular effect shown here. Yeah, and so what do we do? What do we do when this happens to try to make our holes more round? Essentially, if this is a perfect circle and it was printed, your actual part, this is kind of like what the roundness plot looks like in your actual part because of the overcuring. But if in our CAD, we made the part more elliptical looking, so we kind of shaved off the bottom of the circle, then in our actual part, you get a much better roundness. So yeah, that's very critical to design thinking when you're positioning your part. So this doesn't just happen in SLS. This is a problem that happens across printing technology. So for example, in FDM, and if this is your Z part and you have a hole there, then there's kind of a bridging that happens over kind of this void, this air void, and that kind of creates could create some not warping, but like some bowing in that area. A similar effect does happen for the polyjet machine, but it's a lot less visible on this axis because the layers are so small. There's this particular part was printed with a 16 micron layer. And in our SLS parts, that part I showed you before, that was a 100 micron layer. So you can imagine the difference visually here. Yes. So also I want to talk about how important part orientation is to the strength of your part. So let's say I gave you a bunch of cardboard and I said, glue your cardboard layer by layer by layer in the Z-axis. And then I said, take really long strips of cardboard and then glue them together. And then I said, in your z-axis, pull them apart against the glue, against the grain here, and then in your XY plane, pull them lengthwise. Of course, you can visually see that it's going to be easier to kind of break these glue bonds. And so this also translates to printing. So the parts that I printed relative to the z-axis, these very small gear bits, they broke off, as well as these tubes. And that could be in part due to the decreased strength as a result of this printing in that axis. Yes, so when we're printing very fine features to make certain mechanisms, we take this into account. Yes, and so I also want to talk about part orientation and how it has an impact on surface roughness. Essentially here, and for SLS, we can choose to print something in relative to the z-axis or the XY plane. Sometimes it's easier to get a consistent surface roughness when you're printing it in the z-axis, because when the layer is curing, it kind of has times to the powder is spread across the bed, the laser sinters it and cures it, and then there's a second for another layer of powder to go across the bed, the laser sinters it and cures it, and that kind of allows this little bit of cooling in between layers. And the surface you're seeing on your z-plane is just kind of the perimeter of your cross section. It's the contour of your cross section. And so as a result of that, you kind of have a more consistent surface roughness. However, when you're looking at something on the XY plane, the final upskin of your part, that is melted on existing full cross sections of your part. So it can have the tendency of being much hotter. And as a result, if it's too hot, there's a chance that the layer above it that's unsintered powder, that may or may not stick to that face. And it all depends on your laser settings, on your machine settings, but it's something that takes a bit more work to calibrate. And then for the polyjet part, sometimes it is more preferable for your surface, for the better surface to be relative to the XY plane versus the Z-axis, because in the Z-axis, you're seeing more layer stepping. And on the XY plane, there's a bit of smearing that happens with the droplets of resin and the curing that takes place after they're deposited. Yes, so lastly, I want to talk about how algorithmic modeling has had a big impact on how we iterate with our designs and make that faster. When we're designing, we're faced with like a number of challenges to get to that final part. So for example, I have here, what combination of different gap thicknesses throughout the element give the best function while still being cleanable? Because you can think there are gaps that are more close to the outside of the element. There are some very small internal gaps of the element, and our blasting media or whatever form of cleaning has an easier time getting to the outside than the inside. So what combination of gaps gives us our best part, and how do we get there the fastest? Also, let's say we want to have a cool mechanism in our part. Then sometimes it's hard to understand what is the best spring design that gives us the best mechanism. So I have, what is the best design for compliant mechanism for input A to create output B? And so what thickness, what design, how do we get there quickly? And lastly, when we think about connectors for Lego elements, what dimensions give us the best final clutch power, that best feelings? How do we get there the fastest? And so that's where algorithmic modeling comes into play. I took our fun clock and I put it through, I was able to model it so that a number of different features, I could easily change the dimensions of them. So for example, I was just changing the dimensions of the gears and of our little spheres here. And through algorithmic modeling, I can very simply, boom, create a build job that has a number of different gaps with the gears, with these spheres, and then also just extrapolate this. This could be relevant to all the other gaps in our element. And I, boom, create 59 different samples with 59 different combinations. And I can test all of these samples relatively quickly within one print versus having to do 80 prints to get the best combination of samples. So just kind of designing and thinking in this way has really helped us speed up our processes. And yeah, is really going to have an impact in the future. So that leads me to our last slide. Essentially, you know, we've already launched 3 elements, and we're just continuing to look for more opportunities to best apply AM in the Lego context. To best make an impact on the Lego group as a whole using additive manufacturing. I also just wanted to drop that, again, there's a career fair that's happening later in the conference, and currently there are internships in student worker positions open, as well as an AM process engineer. And just to learn more, go to the career fair or look on the Lego Careers website. And yeah, that's the presentation. There's a couple minutes if you have any questions.
Yeah, there are some questions. Actually, I can directly hand them over to you. So the first question that we got, what was the most exciting part that you have ever printed during your time at Lego? Do you still remember that?
The most exciting part. I mean, I think all of the parts have their degree of excitement because it's like, so many years ago, Lego invested in injection molding and went from making these wooden figures to injection molded parts. And now we've just made 3 additive manufactured parts. And so it's kind of like making history a bit. I think maybe the most exciting, and I think the team would agree, might be that most recent duck part because yeah, it was really a big team effort and all done within Denmark. Yeah.
Yep. Another question. We have like 2 more minutes. I try to ask as many as possible.
Sorry.
What was the now? How are the algorithm methodology expressed in Rhino 3D or Grasshopper? That was another question.
How is it expressed?
How are the?
Yeah. Yes. So it's kind of it's not a simple answer, and it's probably a bit confidential how we're like specifically making our models that allow us to quickly iterate that fast. But just using tools similar to Grasshopper is really advantageous if you're doing a lot of iterations. Yeah.
Okay. Then thank you so much for your time here on stage and